Okay, folks, we're doing some heavy lifting here, but we're going to get to some results that are probably somewhat familiar to us qualitatively. And so that is the very famous Heisenberg's uncertainty principle. So let's talk that out. So as it turns out, all of this bizarre math has a consequence. So the consequence of the superposition, expectation values, and so forth has led to the famous Heisenberg uncertainty principle. So here are Werner Heisenberg's words himself. It is impossible to specify simultaneously with great precision both the position and momentum of a particle. And so the idea behind that is if the position is precisely defined with a large number of superpositions. So let's just stop right there and think about that for a second. If position is defined with a large number of superpositions, as we can see right here, and this simulation that I did, right? When I scale that back down, when I have less terms in my basis set, I have a wider superposition. When I increase the terms in my basis set, I have a very narrow superposition. We refer to that as the wave packet, okay? And so what ends up happening now to get that narrow, very sharply defined wave packet, we had to very precisely define the position. The consequence of that is we lose precision in our information on its momentum. So I like to think of this as the more and more we know where the particle is, the less we know where it has been, and vice versa. So if we look at the case of like n is equal to 1 or 2, we have this fairly large distribution. So that would tell us that our position is not well known. But the consequence of that is our momentum will be very well known because we only have like 1 or 2 expectation values to work out in that case, right? So that leads to the Heisenberg uncertainty principle. The uncertainty in momentum multiplied by the uncertainty in x must be greater than equal to 1/2 h bar. And those uncertainties are given by the RMS deviations. So these are RMS deviations from the mean. So remember, RMS is root mean square, okay? So as it turns out, this is the very specific Heisenberg uncertainty principle related to position and momentum. There is a more general Heisenberg uncertainty principle given by the following. So the uncertainty principle can apply to any pair of observables that are called complementary. So complementary observables have the following property. If I take these two observables, and remember in that specific case, omega 1 was position and omega 2 was momentum. But if we cast that aside for a moment and just think of this generally, two observables are complementary if I operate one on psi, then I take that result and operate again. If switching the order of those operations, right? Now operating omega 1 on psi and then operating operator 2 on that result. If these two things are non-equal, then we say that they are complementary and thus they do not commute. So in other words, if I subtract their result, it will be non-zero. And I know the wave function's missing there, so I want to fill that in just to make sure we understand that that would be omega 1 operating on the operation of omega 2 on psi minus, change the order, operator 2 operating on the operation of 1 on psi, right? So what we just showed here, right, if those two things are non-equal, then when we subtract them, it has to be non-zero, and thus that non-zero result is given by these brackets. We call that the commutator. And now that non-zero result goes into the equation right here. So there is our commutator. And now you notice we've got a couple other brackets. So this whole thing is the absolute value of the RMS of the root mean square of the commutator and I'm just going to point commutator. Okay, so that's a mouthful. So as it turns out, right, if we use position and momentum, the commutator of those two things, which we're going to work through this in class. So the commutator of position and momentum is given as I h bar, so it's a non-zero result. And thus, when we plug that in, taking the absolute value of the root mean square of I h bar, we simply just get 1/2 h bar, right? The I squares out and becoming -1, and the absolute value of that is just 1. So this is how we get to that famous delta p times delta x is greater than or equal to 1/2 h bar. So that's all I'm going to say about this for now. We're going to explore the consequences of uncertainty principle as we build up the structure of an atom. And we absolutely have to consider Heisenberg when we're trying to build up a wave function of a realistic atom.